Okay, welcome to Thompson's class. In this class, I'm going to explain the solution of the previous video that I published earlier today. So I'm going to take time to apply this Newton's law of cooling to this particular problem you are seeing on the screen right now. Well, before you start, please, I would really like you to uh, click on the subscription button. Just tap on that subscription button and don't fail to likes and comments, okay? So that every of my video will be able to have access to it. Because I'm very sure it's going to really help in your mathematical pursuit. All right, let's get started right now. So I will start by refurbishing the previous video equation we derived, and then I will use a kind of little transformation that I'm going to do here to make it make more sense that you can understand better. And then finally, in this video, we will solve the problem you are seeing on the example there on the board, on the screen. Then, of course, if you have the comments, you can, or any question, you can place there on the comment section of my YouTube channel. All right, thank you very much. Let's get started. Newton's law states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding temperature. Okay, provided that difference is not too large. All right. So, okay, if the temperature of the object is T, assuming we have T to be the temperature of the object, temperature, temperature of the object. Okay. Okay, and then let T sub S be the temperature of the surrounding. We can, okay, and then let's also define let me manage the space and say let a small letter t be time, be the time. All right. In this case, from Newton's first law, it implies that the rate of change of the temperature of the body, okay, that's the rate change with respect to the time change is proportional to the surrounding changes, temperature of the object, okay, minus the temperature of the surrounding. All right. This also implies that the T over the small letter t is going to be equals to K into T minus T subscript S. I'll talk about this later. So in this problem, once you know the value of K, off you go, the problem is halfway solved. So let's continue by saying that so this is what the differential equation is. Don't forget, not everything is a constant here. The only thing that is a constant here is the Ts is a constant. The temperature of the object is constant. It's a constant. So also, the T is a function of time, temperature of the object, which is a function of time. It's a function of time, meaning that as the object stays, it shares the temperature with its surrounding as time passes. It's the function of time. Okay. All right. So, of course, that makes this a differential equation. So, differential and this kind of differential equation is a first order differential equation because this is the first derivative of the variable t with respect to the time. Okay. All right, so let's go on and rush the problem. So to make it look similar, I would like to use a very, very simple convention. I would like to introduce another kind of t, and I said let this t equals to capital the functional base over t of s. So I can say, note, I'm just introducing that this new t that I'm introducing can be equals to a naught that we introduced in our previous video. That means is the initial value solution at the time. Okay, let's call h of t of 0. All right. At the time, so at where t equals to 0. Otherwise, you will say that T is equals to this new conventional T plus the surrounding temperature. So I would like to use this as my question one. So from the video, from the question on the screen, I would like to start to substitute. At time equals to 0, at t equals to 0, we have capital T of t, which is the same thing as t, is equals to 185 degree Fahrenheit. Also, T of S is given by I think 75 degree Fahrenheit. Then, okay. So that means at time equals to 0. So we can say A naught which equals to T minus Ts, which is the same thing as the function of my new variable T. So that means A naught equals to 185 degree Fahrenheit minus 75 degree Fahrenheit. Okay, by so doing, we will have that A naught is equals 110 degree Fahrenheit. So remember, when we were doing a previous video, we obtained the population size. So in this case, we shall substitute the temperature. So the temperature as a function of time, which I defined earlier, is equals to A naught by exponential KT. Now, this is what it is. This is what it is. It's an exponential growth. So it follow like an exponential growth function. So and then because of the convention earlier in our equation one, so I can say plus Ts of the problem. So therefore, we have T of T is equals to 110 degree Fahrenheit minus KT plus 75 degree Fahrenheit. All right, so let's call this equation 2. Let's call that equation 2. It means wasting much time. We can also see that we've obtained a substitution that makes sense according to how that problem was set. All right. So now let's find the solution of the A section of the problem. So now what the A section says, what if the temperature of the object, in this case Turkey, is the temperature of Turkey is 150 degrees Fahrenheit. So if T of T equals 150 degree Fahrenheit. Now, after an hour, so that means at small letter t equals to 1.5 hour. And you know, how an hour is 30 minutes. Okay. Then what will be the temperature? What is the temperature after 45 minutes? What will be the temperature after 45 minutes? What will be the temperature? So if the temperature of the turkey is 150 degrees Fahrenheit, after an hour, what will be the same temperature? So we say, I can put that notation as after t equals 3, and t of t is going to be equals to what? So that is what the interpretation of that problem. So from that equation 2, from 2, from question 2, you have that 150 degrees Fahrenheit, 150 degrees Fahrenheit is equals to 110 exponential minus k into 30, because the time is 30 minutes, then plus 75 common temperature of the surrounding at time t0. So if you make this here subject of the formula, we can say that it implies that 110 exponential minus k, sorry, exponential kt, there's no minus there yet. The exponential kt, so we have that will be k of 30 equals 105 minus 75, all defined in degree Fahrenheit. Okay, so let's move on. So by this convention, we can have that 110 exponential 80k, 80k, okay? 80k will be equals to 105. That will be 150, remaining plus 150 minus 75. 150 minus 75. So that will still going to be 75 degree Fahrenheit. Wow. So by dividing both sides by the constant here, the coefficient there, you have 101 degree Fahrenheit, because this was the temperature also. 2 degrees Fahrenheit, degree Fahrenheit. Please take care of this, and this cancel and cancel. So we can, of course, see that will be 15 over 22. Okay, so therefore E of 30K equals to 15 over 22. Therefore, introducing log of base E to both sides, log of base E to both sides of this, to both sides, we will have, if you do that, so that we can eliminate this, if we can deal with that, we will have log of E 80K with E of it equals to log of base E of 15 over 22, which is the number in this case. That implies that these will be equals 30K equals to log of 15 over 22 exponent, and which means that I said therefore dividing both sides by 30, it will be equal to 1 over 30 over log over 15 over 22. 15 over 22 inverse E. And what that gives us is, if you use your calculator, that will give us 0.01 approximately 28. But that is a constant, so it doesn't have any units. That's a constant, it doesn't have any units. So what next do we need? Is for us to write the original equation of the problem again. We're going to write that original equation of this very problem again in its real form, where all the constant value k is completely defined. T of small letter t. Small letter t is now equals to 110 degrees Fahrenheit, and again 10 degrees Fahrenheit exponential minus 0.0128128 t, and plus 75 degree Fahrenheit. So I don't know. Let's go check where I can end my question and stop. I think I'll stop at equation 2. So I'll call this my equation 3. So dot, 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 3. All right. So right now, we've gotten the value of k. Remember, we want to find the value of t of t when t equals to 30. So now we can just do that by substituting t of 30. Sorry, t of 45 minutes when t is 45 minutes. So when t is 45 minutes, when t equals 45 in minutes, then what will be the value of t of t? I have to be checking the conversion we use. So that is actually what we were trying to tell you here. So at half a minute, we have a certain convention. So after 1 minute, what will be the value of k? And then we have to find k here, not t of t. Find k. So by so doing, we've obtained the value of k right now. So the next thing we want to obtain is the value of t at 45. So we have when small letter t, that is the time, is 45 minutes. Now, what will be your value of t of t? What is that value? It's the time to do that. All right, let's look at it critically. Now, I will just do the substitution. T of 45 is equals to 110 degree Fahrenheit exponential minus 0.0128 times 45. Okay, because T now is 45. So plus 75, all right? So I'll go ahead and evaluate this. You evaluate this using your calculator. You will obtain the value nothing less than 136.83 degree Fahrenheit. Okay. So that is the A part of the question. That is the A part of the question. So the B part of the question is telling us something else. The B part of the question says the B part of the question is saying, will the temperature of Turkey, when will Turkey have cooled to 100? So that means what will be the time at when the temperature of Turkey has relaxed down to 100 degrees Fahrenheit? So how do you interpret that? So B, if T of P is equals to 100 degree Fahrenheit, what would be the value of T? Or what is T equals to at that point? So we will go ahead and solve this problem accordingly. Again, figure out the solution. Please, one solution we're trying to express earlier on before. So to do that, we are going to use our equation 3 derived just not long, and then we do the substitution for that T of T, and then we do the necessary. So what we mean there is we have 100 degree Fahrenheit 3 equals to 110 degree Fahrenheit exponential minus 0.0128 times T. That is our equation 2. And then plus 75. So again, I'm going to make here subject of the formula. So 110 exponential and 0.0128 and T is equals to 100 minus 75. That is about 25. So let's just evaluate that step by step. And then we have 100 minus 75, all measured in degree Fahrenheit. So which is equals to 25 degree Fahrenheit. Okay, so now we have to divide both sides of the exponential coefficient by the constant value. About that 1 to 18. So divided by 110 equals to 25 over 110. And although it's not signed because that doesn't really make sense right now. So this cancel this, and 5 come here 5 times, and then 5 come here 2, 5 come here 5 is 10. And then sorry, not 5, 2, 2. That is 22. So that would be 22. Okay. So now it implies that exponential minus 0.0128 and t is equals to that value 5 over 22. So the next thing we'll do here now is that we are going to um, uh, take the logarithm to base e, the both side of the equation. We are saying that we're going to take the logarithms of e to both sides of the equation just to deal with this e. So, and we have log of base e of e minus 0.0128 t equals to logarithm of base e of 5 over 22. 5 over 22. Okay. So, and then that will, because the base and the number are the same, so the logarithm can also be done as minus 0.0128 t equals to this value of the log plus E 5 over 22. So as such, that log is equals to that log is equals to that log is something as just go ahead and divide as T is going to be equals to minus log plus E 5 over 22, 5 over 22. Sorry, my story is being already destroyed. I'm going to take care of it. Divided by the coefficient of t that is given in both sides by that coefficient. That is 0.0128. If you do that, what you have there is 115.75 okay, minutes. So that is exactly the time that approximately the time that you will have the temperature of the object, to be precisely in this case, to be equals to 100 degree Fahrenheit. So the way this answer is, I'm not really satisfied because a layman may not really understand. So the first thing I'll do is to divide this by 60. Do that by 60. Okay, that will give us one. That means we'll have 1 hour. Okay, 1 hour. Then the result again of the following, we divide again by 60. That will give us about um, 55 minutes. 55 minutes. You know, every time we divide by 60, we divide it downward. And then divide the result by 60 again. And then you will have 48 seconds. 48 seconds. So we will have about 1 hour, 55 minutes, and 48 seconds for the um, temperature of the objects on the table to cool down to 100 degrees Fahrenheit. Okay, I believe that is what I have to show you in this very video. I believe the video is helpful. I believe you really understand that. If you have any question, do well to drop that on my comment section so that I'll be able to respond to such observation. All right. And also, please don't fail to subscribe to this channel that as the new video is popping up, you'll be able to also see, like, and please comment. Thank you very much.